What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of understanding the internal mechanisms that underpin the performance of large language models, LLMs, specifically focusing on the dynamics of individual tokens as they traverse through transformer blocks. The method aims to trace the dynamics of tokens and linearize the system through Jacobian matrices to uncover properties such as residual alignment, RA, and transformer alignment, TA, in LLMs. By analyzing the alignment of singular vectors of residual Jacobians and studying the layer-wise exponential growth and linearity of trajectories in LLMs, the method seeks to provide insights into the mathematical properties of LLM transformers and their connections to generalization. Additionally, the method aims to explore the relationship between alignment of residual Jacobian singular vectors and generalization performance, ultimately aiming to enhance model performance by amplifying transformer alignment in LLMs.
How does the proposed method or algorithm work, and illustrate it step by step?
The proposed method works by analyzing the dynamics of individual tokens as they move through transformer blocks in large language models, LLMs. The method focuses on two key properties, transformer alignment, TA1 and TA2. TA1 is demonstrated by measuring the expo distance of hidden trajectories, showing that distances between consecutive layers grow exponentially instead of linearly with depth. TA2 is illustrated by examining the alignment of singular vectors of residual Jacobians across depths, which emerges through training and correlates with improved generalization performance. To illustrate the method step by step, 1. The method linearizes the system through Jacobian matrices of transformer blocks, denoted as J_L_I, where L represents the layer and I denotes the token. 2. Singular value decompositions of these Jacobians are computed, yielding matrices U_L, S_L, and V_L. 3. The alignment of singular vectors is measured by analyzing the misalignment of A_ij, k, quantifying how far they are from being diagonal. 4. The expo distance of hidden trajectories is calculated to demonstrate TA1, showing exponential growth of embedding norms as they pass through layers. 5. The line shape score, LSS, is used to quantify linearity in intermediate embeddings, indicating how collinear the trajectories are. 6. The trajectories of tokens are visualized through a two-dimensional principal component projection to observe their dynamics in high-dimensional space. 7. The method then evaluates the correlation between the alignment of residual Jacobians, singular vectors, and generalization performance across various LLMs. 8. It also examines the impact of training on the emergence of residual Jacobian alignment, linearity, and exponential growth in hidden trajectories. 9. The method compares the properties observed in LLMs to those in ResNets, highlighting similarities and differences in their dynamics. 10. Finally, the method acknowledges limitations in the analysis due to constraints in training resources and independent training of LLMs, emphasizing the need for further research in this area.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include gaining a deeper understanding of the dynamics of individual tokens as they move through transformer blocks in large language models, LLMs. By analyzing the residual Jacobians and their singular vectors, the method uncovers properties such as alignment and exponential growth in hidden trajectories, providing insights into the inner workings of LLMs. This understanding can lead to advancements in the mathematical properties of LLM transformers and their connections to generalization, as evidenced by the correlation between residual Jacobian alignment and improved benchmark scores. Additionally, the method sheds light on the regularity and linearity of hidden representations in LLMs, which can aid in enhancing model performance and training techniques. Practically, these findings can inform the development of techniques to amplify transformer alignment, potentially leading to improved model generalization and performance. Understanding the relationship between training methods and the regularity of representations in LLMs could have significant implications for the enhancement of LLMs in various language tasks and applications.
How is the method validated or tested?
The method is validated or tested by examining the properties of the transformer blocks and the relationships between them through the analysis of linearizations of the blocks given by their residual Jacobian matrices. The Jacobian matrices for each transformer block are computed, and their singular value decompositions are analyzed. The alignment of the top singular vectors of the Jacobians across depth is observed in trained LLMs, demonstrating the presence of transformer alignment, TA2. This alignment emerges through training, as evidenced by the distinct diagonal lines present in the matrix subplots. Additionally, the average alignment, negative misalignment, across prompts in the evaluation datasets is measured, and the negative misalignment values are plotted against the benchmark scores across several LLMs. The results consistently show that an increase in alignment corresponds to an increase in benchmark scores, indicating a strong relationship between stronger alignment of singular vectors of residual Jacobians and improved generalization performance.
What results were achieved with this new method?
The new method achieved several results in the study of large language models, LLMs. Firstly, the study uncovered transformer alignment, TA, characterized by two properties that consistently emerged with training in 38 LLMs, including the alignment of singular vectors of residual Jacobians across depths and the exponential growth of hidden trajectories through the transformer blocks. Secondly, the research demonstrated a correlation between increased alignment of residual Jacobian singular vectors and improved generalization performance in LLMs. Additionally, the study revealed the presence of linearity in hidden trajectories after training, as evidenced by the line shape score, LSS values. The analysis also showed that the hidden trajectories in LLMs exhibit layer-wise exponential growth, distinct from the equidistance observed in ResNets. Furthermore, the study highlighted the impact of training on the dynamical properties of hidden trajectories in transformers, emphasizing the importance of training in shaping the behavior of LLMs. Overall, the new method provided insights into the mathematical properties of LLM transformers, their connections to generalization, and the effects of training on the dynamical behavior of LLMs.
What are the limitations or drawbacks of the method?
The limitations of the method outlined in the paper include the restriction to pre-trained LLMs and those fine-tuned on them due to the significant compute resources required to train LLMs of the size studied. This limitation hinders the ability to directly compare models that are trained independently of each other, leading to challenges in understanding the varying levels of regularity between LLMs. Additionally, the lack of careful control over different experimental parameters during training further complicates the comparison between models and understanding the causes of differences in model properties. Despite these limitations, the consistent emergence of properties such as residual Jacobian alignment and linearity in trajectories across LLMs presents intriguing avenues for further research and exploration.